Massoulié is ready to give us our last presentation of the workshop.
Yes, I'm about to start when this ends up working. It's on two screens. That's my. No, it still doesn't work. Sorry. All right. Thanks to all of you for being so brave as to stay till the very end. So I'm going to talk about two distinct problems that are motivated by peer-to-peer systems. One has to do with flows and the other one with matchings. First one is about joint work I did with Dan Thomson, and second one with Bo Tan. And I'd like to make a disclaimer up front that this is fairly recent work, so there will be more questions asked than answers given by the end of the talk. So let's see. So first, quick overview of the two problems at hand. The first one is about peer-to-peer live streaming systems. These are systems that are widely deployed and used to watch live content on the internet. So you have systems like PP Live, for instance, which is massively popular, which has been developed in China, and it broadcasts many channels of Chinese TV, for instance, across the world. So the purpose of these systems is the following. There's a source somewhere that injects content, and all of the nodes who are interested in it connect to the system. They organize themselves in a logical topology with edges connecting them, and over the internet, they exchange pieces of information so that ideally each of them receives every packet of information injected by the source after a reasonable delay so that they can play back the stream. So it's TV over the internet. So this is how these things look like from the application viewpoint. It's a management of a logical network and exchanges of information along these logical links. So there's been a lot of work about the scheduling decisions that one needs to make in order to make sure that everyone indeed receives everything, and a little less work on the delays incurred, and even less work on a more recent concern with these systems, which is the so-called ISP friendliness. So just to let you know what this is, I should perhaps start reminding what network neutrality is. So this is network neutrality is the requirement that all applications should be treated equally by the network service providers or the ISPs. In particular, peer-to-peer traffic should not be discriminated against compared to web traffic or whatnot. And the answer of the ISPs to that is to say this is unfair because you ask us to be neutral between several types of traffic, but these peer-to-peer applications are completely unaware of our own constraints, and what we do when we prioritize some traffic against some other is that we are trying to save the quality of experience for web traffic, say, or mail, whereas these peer-to-peer systems do not respect the underlying network conditions. So they say we don't want to do network neutrality unless at least the peer-to-peer streaming systems are ISP friendly. That means they are aware of the underlying network resources. So here's a picture of what the underlying internet might be. There would be two ISPs in that example, and then the logical flows on the top picture would in fact correspond to paths on the internet crossing several routes, several links. Internet service provider. So that's like BT would be one here. And so it's notorious that these guys are very concerned about the peering links that they set up amongst themselves. So the red link here would be an expensive resource, and you'd want to ensure that everyone receives everything from the source by not harming the most critical resources. So the concern here is to ensure the live streaming operation, delivery of the data, but while not overloading the critical resources. All right, so now, yes, that's what I just said. So the second problem I'd like to discuss next will be about video on demand, which is a different application where users want to watch something, but they are not synchronized as they were in the live streaming applications. So demands might arrive at any time for any particular content. And so what has it to do with matching? Well, if you have a collection of users who have some particular contents that they are able to serve, then the question of the matching is to determine which one of them is going to serve which content given demands. And so we're not so much concerned about how to set up a matching to cope with the demand as to determine what content these users should be maintaining in their local memories, so that in the end we manage to serve as much as possible from the incoming demand. So I like to think of this problem as one of changing the schedulable region so that it incorporates as much as possible of the incoming requests. In fact, you could think of it a little differently, and there are strong ties, I guess, with what Jean presented this morning. Okay, so let's get started with the first problem, that of live streaming. So my aim is to explain you a so-called implicit primal dual algorithm that we've developed to solve the problem, and describe some partial results and a bunch of open problems about it. So here's the problem formulation, which is quite standard, I would say. So we have a graph which contains the source as well as the collection of receivers of the flow of information. And there's an injection rate at the source. And then the control variables that we need to select are the rates at which data is sent over each such edge. And eventually we want to do that while minimizing the cost incurred by the network. So formally, we want to minimize this cost over C such that the broadcast of information is feasible, and which can be formalized by requiring that for any cut separating the source from some receiver, the flow through the cut is at least the injection rate. So in the case of broadcast, which is what we are discussing today, this is the fact that these cut conditions are necessary and sufficient is what's called the Edmonds theorem, proven in 1972. And it's a fact that you don't need to do any network coding to achieve this broadcast at rate lambda when the cut condition is met. If, on the other hand, you have relay nodes and not just receiver nodes, the cut condition is again necessary and sufficient, but it requires, in general, network coding to achieve this streaming rate of lambda. All right? So examples of cost functions might be sums of costs of underlying physical links, and this cost might be a function of the flow through that link. So that's the typical thing. And this could be a combination of congestion cost related to the delay or to the packet loss at that link, as well as a cost that is some operational cost that the ISP, say, makes known to the user. For instance, this red link in the previous picture might incur a linear cost with a strong proportionality constraint compared to the other links. All right, so a little bit of a background on the problem. So network coding experts have looked at this. There's a very interesting paper by Desmond Loon et al. In 2006, which tries to come up with algorithms for setting the link, the edge capacities so that streaming is feasible while, sorry about that, while the, right. So they basically introduce new rate variables per receiver, and then they implement some kind of back pressure control per receiver, and in the end, they determine the rate at which you should use an edge as the maximum of the rates determined for each individual receiver. So this lends itself to a distributed implementation. Why do we still want to work on the problem? The issue with their result is that it's quite delicate to implement if you have a large dynamic set of users. For instance, PP Live has routinely tens of thousands of users watching the same channel, and they come and go. So if you were to implement this kind of scheme, you would need to maintain control variables at each member of the broadcast group and update these as they come and go. So this is not really feasible. All right, so to introduce the option we are proposing, I'm going to recall the classical primal dual approach to solving the original optimization problem. So it would require setting up a dual variable per cut constraint and let it evolve as per the first equation. So it would increase according to the injection rate and then decrease according to the cut capacity. And then you have, so that's the dual update, and you would have a primal update for setting the rate Cij, which would be given by the second equation. It would increase according to the dual variables and decrease according to the marginal cost of loading some extra traffic on the edge Ij. So we'll be assuming that this Pij is available to the users. So that's the common assumption in the literature on transport, on TCP, on congestion control. When this is a congestion cost, if there is an extra management cost, as in the ISP friendliness problem, then I mean the discussions that the ISPs are having these days are exactly about how they might inform the users of the management costs of communicating between any two users. All right, so we'll assume this is known throughout.
So I don't understand. So outside the brackets, there is the bottom index, say
All right.
CIJ or plus, and some US or plus. What do they mean?
So the meaning is that if the quantity you're updating is positive, you ignore the brackets. If the quantity reaches 0, you have a reflection at 0. So this is saying that you reflect when Cij is at 0, and the top line, you want the multipliers to be non-negative, so you reflect when the multiplier is 0. So that's just reflection at 0. I don't know who invented this notation, but it's very convenient. And so this does converge to the optimum, but the problem is that it's not practical as it has exponentially many dual variables. So we don't want to implement that. We just want to note that it brings about Q-like dynamics for each of the quantities. So the dual variable mu sub s increases at some rate lambda, drains at some rate, which is the capacity of the cut, and reflects at 0. This is exactly a Q with arrival rate lambda and service capacity, which is the cut capacity. So we'd like to leverage that and have some implicit implementation of that, which somehow interprets some backlog somewhere in the network as the multiplier associated with a cut constraint. Right, so that's our proposal. So we don't maintain explicitly any dual variables. Instead, we interpret the candidate from US will be the information that is replicated at all nodes in set S and nowhere outside. Okay, so that's a natural one. And this has the following desirable property. If you want to use the primal update rule, you had a summation of quantities which were the multipliers of all the cuts which separate I from J. And so now if we have this interpretation of the multipliers mu sub s as the quantity of information replicated precisely at the nodes in S, we can measure this sum of multipliers as precisely being the amount of information that is present at node I and not at node J. So this is something that they can locally figure out between themselves by exchanging bitmaps or whatnot to figure out what each of them has. So that's it. It's not a complete description because I've not told how packets get scheduled, and this is what we want to do next to see if we can make this work. We'll see. So first attempt to see what the issues might be with implementing this program is to try the so-called random useful packet selection, which is something we had come up with together with Andy Twig in the same context but without a cost minimization objective. So it's really simple. When you want to send something from one node to another, you pick among the packets of information that you have and that the receiver doesn't have, and you do that uniformly at random because you don't have a clue what's to be sent. So just send something useful chosen uniformly at random. So that's our starting candidate. And then to craft a stochastic model of that, we assume at the source node there are Poisson arrivals of fresh packets at some rate lambda. And then the transmissions along edges take place according to this random useful packet selection. But the transmission rate is according to Cij. So we have Poisson with varying rates. All right, so we don't know how to analyze that. This is so messy. We resort to fluid limit approximations, and the interpretation of the fluid limit we are taking here is to assume that the packets become smaller and smaller. So as we let packets become smaller and smaller, we have some law of large number effects, and we can write down a set of deterministic equations for how the state variables evolve. So the state variables here would be, we have the Cij, the things we want to control, and then per set of nodes we have the X sub S is the set of the amount of information precisely replicated at all nodes in S and nowhere outside. So maybe it's too late on a Friday afternoon to go through these. I mean, if you look at Y sub S, which is the amount of traffic that is replicated nowhere outside S, this increases at rate lambda, this decreases at something that is smaller than the cut capacity, so it's close enough, but it's not the dual update rule that in the primal dual algorithm we would have. But it doesn't quite do the job as the counter example here shows. So this is a simple toy network with two receivers, symmetric, and we have three edges here, three links, and the ideal, the cost optimal way of sending data here is to send half of the data to each receiver from the source, and then they exchange the other half among themselves. So random useful is failing to identify that precisely because it does not coordinate. You know, if you take a cut and you look at what gets sent along each edge crossing the cut, random useful is too distributed. There's no synchronization, so the same things might be sent along several edges through the cut. And this is what happens, which leads to a slight overutilization of the first link. So random useful does not work in combination, even though it seemed an interesting candidate. So this leads us to eventually consider random linear coding instead. So we don't exchange packets anymore, but linear combinations of packets. And we take them randomly with a uniform coefficient, say. All right, so the state variables now become a bit different. We are going to go through a fluid limit analysis once more. The state variables are now the subspaces spanned by the vectors held by nodes. So V sub S is the subspace spanned by all the encoded packets at nodes in S. And for getting at fluid limits, we will be working with the codimension of this set. So V sub little s is the space held at the source, so this is the largest possible space. And that's what everyone is trying to obtain eventually. And so y sub s is the codimension of, all right, so it's the dimension held at the source minus the dimension held outside of set S. Oh, okay. And we still have the same kind of primal update. And now the back pressure that drives the primal update is a difference of two dimensions. So that's the dimension held jointly at I and j minus the dimension of packets held at j. So this is essentially the number of degrees of freedom that I can contribute to j. So that will, if you want a fancy name, you can call that algebraic back pressure. And this is something that has been used for a unicast. That's something that Muriel Médard mentioned earlier this week. They have worked on using network coding for TCP, and this is the kind of measure of lateness of the one node with respect to the other that they use. Perhaps one last comment about that. This is reminiscent of back pressure, as in Tassiulas and Ephremidis' work for controlling rates in a single commodity flow with a single receiver. So now the difference is that as we send along an edge, we keep a replica of what we've sent at the sender side. All right. So this is similar but different because we are not after a unicast, we are trying to do broadcast. So fluid dynamics, again the small packet limit. This looks much neater than with random useful. So we have for the y sub s variables I just introduced, trying to capture the information nowhere available outside of set S. This increases at rate lambda, this decreases at the cut set capacity, except for some reflection term. And the reflection term is, so it's captured by the second equation. Basically, there's a monotonicity among these y sub s variables, and you're not allowed to let one y sub s go below the corresponding variable of a smaller set. So a few comments before I can describe what we are able to achieve and what we what we need to conjecture instead. All right, so the state variables, these are the codimensions of sums of vector spaces. Okay, so this constitutes a convex cone. That's not hard to see. However, the structure of the cone is unknown except when you have 4 or less nodes, say. So when you have 4 or less nodes, you know that this is specified by so-called submodular inequalities. And then there are these Ingleton inequalities that have been recently generalized that hold for those codimensions and that capture every constraint that these dimensions are subject to. For V larger than 4, I don't have the name of the author who proved that indeed this was the characterization for 4 nodes, but he said he'd given up on 5, right? So he doesn't know if it's polyhedral, if there is a finite number of constraints. We just know it's convex. And these, I mean, the inequalities known to hold for 4 nodes hold for an arbitrary number, but we don't know if these exhaust the possibilities. So it lives in a slightly not entirely well understood space. All right, so what we can prove though is that if you are started at an equilibrium with the right rates and with the right amount of information kept behind each cut, then you don't deviate with those dynamics. So there's one part which is absolutely trivial because that's how we determine our rate update rules, which is to say if you start at the right point, the rates themselves won't change because of the update rule. The difficult part is to show that the codimensions of those weird spaces themselves won't change, right? And so just to give you the key point in proving that is to leverage one structural property among critical cuts in this kind of setup. So if you have an optimal configuration, you take two critical cuts, take the union of them, then you still have a critical cut. So this is something that is, we figured out in the process of showing that. So we believe that much more holds, but at this stage, the only other thing we can prove is the following, that that's for the case of separable cost functions. So we are losing on generality here about the cost function. Then we can show that the dynamics that we described at the fluid level won't diverge. They will be confined to a bounded set. And so we can interpret that as saying that there's a bounded lack of information at each node eventually after some time. So that's a partial result. And the way this is shown is by exhibiting a suitable Lyapunov function. So we tried hard to show a stronger result, namely that starting from anywhere you would converge even for general convex cost functions to an operating point which achieves the optimal rates, minimizing the cost while ensuring feasibility. Simulations certainly seem to suggest that this is true, but we have not been able so far to prove that. So that's stated as a conjecture, right? So before I move on to the second part of the talk, let me just say that this is not the usual way that network coding is made useful. The use of it that we make here is a bit different. Typically, you resort to network coding because it strictly increases the rates that you can achieve by mixing at the right places. So here it's doing something different. It's allowing you to not send redundant data along these cuts. So we saw that there was an issue with the random useful packet scheduling. So with network coding, you don't have this issue anymore. It goes away. All right? So if you have any questions about this, no?
You seem to be working only with dimensions of the spaces?
Yes, yes.
How is that okay? I mean, it's hard to accept that.
So that's you can write autonomous equations for how the dimensions evolve, and actually they are independent of the field size that you use.
But to accept that that is relevant to the original problem is not so easy. Or do you have a theorem like that? Because the problem is really, I mean, you have information, it has some geometry, it's not just dimensions.
Yes, but that's you're trying to use those vectors held by users to determine at which rate to send. So there are several ways to think about it, but one way could be the following. You could assume that users they fake the operation by sending vectors, and they maintain a set of vectors that are not necessarily linked to the actual data they send. And then you would use this emulation of what would happen in a network-coded scenario just to determine at which rate to send. And then you could resort to other approaches to send. I've glossed over another aspect, which is that you don't want to do network coding without introducing new features such as bounded generations, so that, I mean, you could have, for instance, a few missing dimensions but still not be able to decode anything if you don't have strict boundaries on which packets are allowed to be intermixed together. So in practice, either with network coding, you would want to have bounded generations, and then, but still, that would capture exactly the number of packets that you need to receive before you get everything that the source has. I'm not sure I answered your question.
It gets get a better feeling, but yeah, I'm not sure either.
Okay. Okay.
Yeah, so is the fact that you're using network coding that enables you to look at the dimensions, essentially, because you're smearing out the entropy of the packets? Is that presumably is that why it's sufficient to look at the dimensions of the spaces? Presumably.
Well, the dimensions would capture exactly the amount of information that you need to get in order to catch up with the source.
So what happens in practice with the delay that you get for having to wait for the generation to be able to perfectly construct?
So it does scale with the generation size. So you have a compromise there. So we tried several generation sizes. We also tried that without network coding at all. So the first combination, IPD plus random useful that I was describing, which in practice does quite well. So, but if you're really concerned about delay, then you want to take that into account. And this is why what I mentioned, that instead of looking at the dimension of your neighbor and at your dimension corresponding to the actual data packets that you have, if instead you use that as a signaling mechanism that is decoupled from the actual packet transmissions, you could have some kind of virtual backlog that would drive your decisions, and you may be much closer to the source if you don't rely on actual backlogs but on virtual backlogs to control your rates. So that's related to the virtual queue idea of Frank for signaling congestion. Somehow you can also implement this idea and reduce the delay if you want to. Any other questions?
I didn't quite catch what you mean by bounded generation. Is this the idea that if there was just a single giant file and everyone knew how big the file was, you'd do a random linear code across the entire file, whereas if it's a live stream, you have to have a sliding window across which you're doing a random linear code?
Yes.
Is that the same?
The equations I wrote down, the fluid equations, assume you combine over whatever you have from time 0 to the present time. And this is not going to allow you to decode and retrieve and play back the information after a bounded delay after the source. So
it won't allow new people to join into a session. I guess a television station has been broadcasting for years, and people might want
yes,
to
so that's why you need eventually to introduce bounded generations, and then the source chops its content into generations, and you're allowed to mix packets and do linear coding among content of a given generation. But
so
you never mix.
Does the generation depend on the number of people in the session? Does the size of the generation have to depend on the number of nodes participating?
You see, we have fairly partial results, so I can't be conclusive on that. Whether you need to let, I think you from for practical reasons, you don't want to let them grow unboundedly. Whether in theory you start having problems when the number of users increases, I don't know. Okay. All right. So second topic, which is about matchings for video on demand. So here's our model. We have a large collection of users, n, and each of them can store n items from a catalog of a collection of possible items. And they have some limited service capacity, say of one request per time unit, or one request simultaneously. They have a bounded uplink bandwidth for serving requests. And there's also a constraint on the memory they have, which eventually conditions what they can serve. So a stochastic model for that, that will be a very classical one that I'll be describing. It will be a loss network eventually. So is specified by request arrival rates for each item. So
An item is a movie or a packet?
That would be a movie here.
A movie, whole movie.
Yes, 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 yes. So that, for instance, you could think of a YouTube catalog being dispatched across storage spaces at a large collection of users, and then you want to serve YouTube clips from these users' storage and bandwidth rather than going to the data center of Google, which is the alternative, the fallback solution. So, but that would be movies, yes. So to make life simple, we have also exponential holding times with some parameter. We have a system load that we can define, and then we want to know whether the memory available at nodes is going to hinder performance or not. So what is a suitable amount of storage to be provisioned at users, and also how should we place content on each of them so that we can absorb as much of the demand as we can and offload the data center in the example of YouTube. So feasibility of serving a number of requests is captured by a classical result on bipartite matching. So here on the top you have the nodes themselves and with the storage, the content they store. And at the bottom you have one node per content, and each such content has a number of pending requests, say. And so these will be matchable to the top nodes only if and only if the condition given by Hall's theorem is satisfied, which is that taking any set of items, then the number of nodes that they collectively connect to has to be larger than the sum of the number of requests for these items, right? So it's a very classical result. So the consequence will be the following. So now if we assume what in the lost network literature is referred to as a repacking, so perfect repacking. As a new request arrives, you're allowed to shift load between boxes and to absorb the new request if it can be absorbed, and otherwise it gets dropped. So now we can describe this as a lost network where we have for each item set corresponding to the condition in the previous slide by Hall's theorem, we have a virtual link whose capacity is exactly the number of nodes who have some content that belongs to that set. And then for each item type, I have a virtual route that goes through all the sets that contain this, right? So it's just to say that I will be able to accept new calls if and only if I have spare capacity along each of the virtual links that the corresponding route goes through. All right, so that's the classical lost network model. So we know that the stationary distribution is independent Poisson variables per each type, conditioned on feasibility of the route capacity constraints. So I'm going now to describe briefly our assumption on what we would store at each node. And so that will be reminiscent of something in Jean's talk. So we'll have a product form distribution for deciding what to store on a given node. And this product form distribution is justified by the following update mechanism. If a given user replaces a random item in its cache by a requested item, then you have a reversible Markov chain describing what is in a given cache. And that has precisely this product form distribution. So the probability of holding a collection of items is proportional to the product of demand rates for this item. And for simplicity, from now on, I'll assume that each node is keeping a random cache set that is sampled from this distribution. And we'll see that it does reasonably well in terms of making the system able to cope with the offered load. So the idea when I call that demand-driven cache updates is that there's no need to identify explicitly those new sub-I. They implicitly drive the contents that are replicated in the caches, and as a result, hopefully, the load can be served from these boxes, from these nodes. All right, so a first scenario, which is the simpler one, maybe not entirely satisfactory from the YouTube modeling perspective, is to assume you have a fixed item set and a large collection of users. So in that scenario, a natural scaling assumption, if you're happy to deal with only a bounded number of items, is to assume that the request rates scale with the number of users. In that case, it turns out that because of our assumption of random cache selections done in an independent fashion across boxes, then the fraction of users who hold a particular collection of items will converge to something proportional to this product of popularities of items. All right, so it turns out that this is precisely the setup. This falls into a setup that Frank studied in a paper, and this is also covered in his survey on lost networks published in 1991. So when you have a fixed set of routes of call types, and you let the capacities of the links scale linearly and proportionally to the arrival rates per route, then you have a very nice characterization of the asymptotic behavior of the network. And you have a variational problem that helps you determine the asymptotics of the loss probabilities. So we have it, it's off the shelf. You can write down this optimization problem and figure out whether what you did makes sense or not. And it turns out that what it ensures, what you find out is that for each item, the loss probability converges to something that is going to be 0 if the load is subcritical. And that is the smallest loss probability that makes sense given the load if you are in a supercritical network. And this is the same loss probability for any item. So what you might conclude from that is that you have an optimal service capacity using this product form cache distribution. So another thing to notice, though, is that this is optimal, and this does not rely on the amount of memory that is made available to the users, which is a bit surprising. So there's no memory bottleneck here. And this is strongly tied to this assumption of a fixed item set, which is not really what you'd assume in the scenarios like the one where YouTube is to be provided to a large collection of users. So, if you run simulations, you find that the catalog size, the number of items matters a lot. So this is for 500 items, critically loaded network. And even though you accept most of the load, you find that the asymptotics in the previous slide don't quite hold. So for the less popular items, you see quite significant loss rates. But since they are not so popular, overall performance is good. But somehow another kind of scaling would make more sense to figure out what goes on here.
So Laurent, is there repacking going on there?
On this, there is, yes.
And a simulation as well for everything.
Yes, but we've tried various things, and we've tried to repack only, to not repack, or to repack only once, trying to shift only one connection. And interestingly, you get almost the same performance with the perfect repacking or with repacking only once. So it seems to be quite enough to do a minor repacking. This kind of phenomenon suggests another kind of modeling. So here's the one we came up with. So we want a large collection of items. So let's say as many items as there are users. And to have a tractable model, what we are doing here is that we're assuming we want something finite dimensional somehow. So we're assuming a bounded number of item classes, but they share the same popularity among items in a given class. So new sub I now refers to the arrival rate of requests for items of class I. But there are a number of such items that scales with the number of users n, right? So it's not too difficult to see here that you need some memory space that scales with m if you want to be able to achieve zero loss rate eventually when you're subcritically loaded, or I mean to accept the most, you need more memory than in the previous case. That's easy to see because you can figure out that if m stays bounded, then there are some substantial fraction of items that is replicated at most m times, in which case its loss rate can be lower bounded. Okay, I'm not going into that. So first result that one can have for the original network with repacking is that if it's subcritical and if m scales like log n, then you can indeed absorb the full load, right? So I'll say one word about how this is shown. Basically, you pick Poisson numbers of candidate calls per item, and then you check whether you can fit these calls into your collection of caches. You can find a matching, and you use Hall's theorem to write an upper bound on the probability that you fail to match things. So there's an averaging over two sources of randomness. There's the number of calls, and there's the cache contents as well. And so you can work on that, but so it allows you to show that if you have logarithmically many items that you can store, then this can be made small, and you can deduce that the loss network with high probability has a small loss probability. Trouble is it doesn't cover the supercritical case, and you cannot make this argument to work. If you want to show that you can absorb all to work at full speed if you are in a supercritical mode, you won't be able to rely on this argument. It does not tell you either whether the logarithmic memory space is a feature of the proof technique or whether it's required for real. So there's an argument which suggests that you don't need logarithmic at all, and that you do better than what this previous result suggests, and this is as follows. So if instead of doing perfect repacking, we do something far dumber, which consists in, for each incoming request, of identifying the set of nodes who hold a copy of that item, and then we direct it uniformly at random to any of these. Then we get a much simpler system. There's no coupling of load between boxes. And so we essentially have a large collection of decoupled one-dimensional loss networks. They are random because of the content placement, but nevertheless we can work out some bounds on the performance. And what we find is for a given m, as we let the number of items, number of nodes go to infinity, the acceptance rate is going to be the best possible, which is a minimum of 1 n row after scaling, minus something that is a correction term that will vanish if the memory space goes to infinity. So this dumb way of assigning jobs to boxes allows to maximize the acceptance rate up to a correction term. We don't know if the correction term is the sharpest we could achieve. We suspect that if we resort to repacking, then we could make it smaller than what we have with the dumb strategy. But we don't have a proof. I mean, this is way easier to analyze than the system with repacking. So I'm done, basically. So conclusions are that demand-driven cache management, as I described it, seems to be efficient for the large symmetric scenarios, at least the two we considered. So that we don't really know how to analyze repacking for the large catalog case, the second one. But it's not, I mean, not everything is known. We'd like to know, for instance, whether indeed dynamic repacking, load balancing is unnecessary, or that's what we observe in simulations, that you need to do very little and you absorb, you don't need to go through very lengthy repacking sequences to absorb as much as you can. There's also something, I've basically talked about a setup where the cache contents are sampled, and then this is a frozen random environment, and we look at the loss network in this environment. In fact, you'd want to figure out how to arrange the joint dynamics of cache content replacement and call acceptance and rejection. And this we have some results for the small catalog case, but we are not there yet. And what you would really want to address is, in fact, zip-like distributions where you have a power law for popularity, catalogs that are large, and this takes us outside this this model I was just describing. And I mean, we don't have the techniques to handle that, even though this is what we'd want to be able to analyze. All right. So, any questions? It's late, huh?
No, so just to understand, I mean, the cache, I mean, why would the users basically keep those various videos or whatever, just because they have asked for them and so they have them on their computer?
So we'd want I mean, that could suffice. That could suffice if the users are indeed completely homogeneous, interchangeable. They could keep what they have asked for, and if they ask things several times, then this cache replacement mechanism would produce this product form distribution for what each individual has, and that would be one possibility. We are also looking into other approaches where, for instance, as a request comes in, you try to have it served by someone. If no one can serve it, but someone is idle, you could ask this person to store it for the sake of a future demand, and that would lead to a cache update which is not due to this person requesting that content. And I think in practice you'd want to have that if you really want to optimize your system. Yes.
You may actually want to do an overlay servers network, right? Go outside the user servers and introduce your own if you are the provider, and then you can pass the request to there, so you create a hierarchy. And then if those have certain connections, you can actually do it a lot faster than relying on the connection of the users themselves.
Sorry, I did not.
So the topology of the network here is what?
Oh, it's fairly simple. Since I was only relying on matchings, what this meant was that the only constraint was the uplink bandwidth for service, which is reasonably okay if we have users in a metropolitan area, and I mean, you would serve from someone in London to someone in London, and they have if the metropolitan area network is well provisioned, this is the access bandwidth that is binding. So
that's the model. You don't want to create hierarchy where you you use your own servers properly located and then connect it to the users to go to them to facilitate the caching.
I think this is like the first cut to make the system simple and tractable, but indeed you would like to take that to to extend that to introduce costs of serving from one place to another, and then maybe there are other bandwidth bottlenecks somewhere, and
Because that network resource you can control better than the individual users.
yes, but actually the scenario we envision, to have this deployed is to have an ISP provide boxes at its customers' houses and serve from these boxes. So then the ISP would have full control of what it gets stored and.
But I've talked to people that they actually can create this hierarchy and they can do it in a way that's transparent to the setup boxes of the users, right?
Okay.
You don't have to tell them what to do. It's just because the only thing they care is to get the data, the files they want when they want, like the movies. But where you store them, you don't have to store them just on their own set of boxes. You can store them somewhere in the middle.
Okay.
That's what I'm saying. To avoid some of the difficulties you have with the non-exponential demand and other things. You have to make your network match the power laws of the demand.
Okay.
If you can pull from several caches, does it start to look like the multipath problem where you potentially get some benefit by not just pulling one item from one cache?
I think you may have benefits, but it could be that these are second order, because we see that we at least we seem to be doing quite well. Yes. And the second order corrections to what I was describing are not available now, so this is something to look into.
If you go to a zip distribution, where basically says if somebody asks something, more and more people ask you, okay, it's a popularity model. Can that create, this will create a very huge demand for certain parts of the network, right?
But the thing is with this product replication rule, it's typically most users store a cache content that has an aggregate demand that is very well balanced. So so at least this is what happens for the model of request rates I was describing. And this is how we argue to get results. In fact, if you have a zip distribution, I'm not sure anymore. So
You want to create storms in some parts.
yes. So that's why it's challenging, and we'd like to understand. You're mentioning a problem with most popular items. I'm concerned about zillions of less popular items that start polluting caches, and there may be a need for a more subtle scheme that somehow needs to explicitly figure out what's really not going to make much sense to cache and drop some of these contents. So that's why we need some follow-up work to figure out whether this is going to be enough or not.
Can I ask just another question?
Yes.
It's related just because I don't understand exactly. Who are the people who would have those cache?
So that would be users of an ISP, say in the UK, that might be British Telecom, and if the BT users, when they install their gateway to the internet, they also have some attached storage space, then they could offer this storage space, and then British Telecom might decide to use this distributed storage platform to serve a request for content. So that's the scenario we have in mind.
Does that exist, that the provider asks the user for cache?
There's an interesting business model in the United States. I don't remember right now the name of the startup which does that, but what they do is they go to potential subscribers of a broadband service and they say, why don't you go to Verizon and register and subscribe to the broadband service? If you do that, we'll give you a little bit of money, but we'll claim a little bit of the uplink bandwidth and we'll store a little bit of memory there. I think it's called uCloud or something like that. So there is such a startup which is implementing that. So without the agreement of the ISP, but it's happening.
So taking some hint from that, when we were working on similar problems with satellite networks, right? And you had the set-top boxes, and we also were worried about zip distributions. We actually created a hierarchical scheme where you will rank, if you request things, we wanted to do it in such a way so that I don't acknowledge anything. I just watch who requests and who doesn't. Then the popular ones, we will move them around. The unpopular ones, that you could drop or go between the two classes, will broadcast because we could do from satellite.
Okay.
So this way, we were able to do an order of magnitude more items to serve than what a traditional system would do, where you didn't have these two classes. This was our sort of attempt to take care of like very popular versus little popular,
Okay.
and make sure that you can.
Okay.
This system was called air cache and actually was implemented. We were using the air actually as a way of caching by the broadcast.
Okay. That's
So in
interesting.
cable, you can do the same in cable because cable is like satellite.
Okay. I'll look into ACA.
Cable, I mean, not fiber optics,
Mhm.
just cable.
Yeah, yeah. Any more? Thank you.
Thank you, Laurent, again.